Okay, so let's get started with today's lecture. This is the second lecture on physics-informed neural networks. Last lecture, I introduced PINNs to you. And this lecture, and also half of the lecture on Wednesday next week, is all about discussing the limitations of PINNs and also the extensions. And like I showed you, there are so many hundreds of extensions of PINNs, and it's an entire research field by itself. And so we're going to delve into some of these that improve the performance of physics-informed neural networks. So before we get into the extensions, let's recap what a physics-informed neural network is. So this is the key slide from last lecture, and it has all the concepts behind PINNs in this slide. So I'm just going to spend some time just recapping what a physics-informed neural network is. So physics-informed neural networks are ways to solve differential equations or problems related to differential equations. And so the example on the slide here is the damped harmonic oscillator, which we looked at last lecture. And the key idea of a PINN is very simple. It's just to use a neural network to directly approximate the solution to the differential equation. So PINNs work for many different differential equations, not just the harmonic oscillator thing here. And this is what we always do. We say the neural network, which is just a flexible function that takes as input the coordinates of the solution. So in this case, just the time coordinate, because it's a 1D problem. And then the output directly approximates what the solution value is. So this U here, which in this case is the displacement of the oscillator. And typically the network we'll start with is a MLP, a simple fully connected network, for example. And it's really important to note that this is a mesh-free approach. And that means that once we've trained this network, we get a function as the approximation to the solution, which we can query at any point in the domain. So this is different to how, for example, finite difference methods work, where once we've run the simulation, we get the solution on a finite point on a mesh, so discretized on a mesh. Okay, and then the loss function that we use to train the network has these two main components. The first is called the boundary loss, and that makes sure that the network matches whatever the initial conditions and the boundary conditions we have of the problem. So in this case, we're going to make sure that the oscillator starts at a displacement of 1 and has a velocity of 0. And so to get the velocity, for example, we just take the gradient of the network with respect to time. And then the important component is the physics loss. And this is minimizing the residual of the differential equation itself. So we know from the differential equation, this left-hand side should equal 0. And so we evaluate all these gradients that we require to evaluate that left-hand side using the neural network. And we try and push that residual to 0. So kind of intuitively, boundary loss makes sure that the solution that the network learns is a unique solution. And the physics loss makes sure that the underlying differential equation is obeyed at every point in the domain. So we evaluate this at many co-location points, these green points in the domain here. So as I said last lecture, this is a really key slide to understand. So has anyone got any more questions on the basics before we move on? Hopefully it should be clear by now. Okay. So yeah, I told you that PINNs are a general purpose technique for solving many different differential equations. And so this is an example of using PINNs in 2 dimensions to solve the 1D Burger's equation plus its time evolution, so 1 plus 1D. And I'm not going to go into this in detail, but the only difference here is now we're sampling boundary points across the whole boundary. So instead of just needing one boundary point, we need many. And we sample co-location points in the entire domain. And we explain that this is kind of an interesting problem to study because it forms a shock in the solution, which traditional numerical methods often struggle with. And so the PINN seems to perform fairly well in this case. And then last lecture, I talked about all the different types of problems that we can solve using PINNs. And we can not only solve forward simulation tasks, but we can also solve inverse problems where we're given some observations of the solution. And we want to understand what some underlying parameters of the differential equation are. So these phi parameters here. So for example, in the damped harmonic oscillator, it could be understanding what the coefficient of friction is, or the spring constant. And the way that we can solve these inverse problems is that we have this extra data loss term where we match the network's output to the observed data points that we have. And then when we're training the PIN, we do a joint optimization where we both learn the parameters of the PIN, theta, and the underlying parameters of the differential equation phi jointly in the same optimization algorithm. And then you can take this concept further and even try and start to learn the underlying differential equation by learning the individual coefficients for each term in the differential equation. And so this is how we can use PINs for equation discovery. So in this case, we have phi here now is a vector or a library of differential operators. For example, all the gradients that you might think would appear in the differential equation, so d by dt, d by dx, etc. And then lambda here is a matrix which contains all the coefficients of that PDE. And we typically, so we do the same thing as an inversion. We match the network to some observed values of the solution, and we jointly optimize the coefficients of the PDE here to try and learn the underlying differential equation. Now, this problem is often very ill posed because there are many different combinations of PDEs that the data could fit potentially. So we often add like a regularization, like a sparsity constraint to say we want the equation that has the minimum number of terms to be the one that we choose. Okay. So we're on the second lecture of PINs, limitations and extensions. Like I said, I'm also going to do half of the next lecture is also going to be on extensions of PINs. I'm going to give half of that lecture, and then Sid's going to come halfway and give the rest of the lecture. And he'll talk more about the theoretical aspects of PINs. Then we're done with PINs, and we'll move on to another big topic in SciML for scientific machine learning, which is operator learning. Okay, so I've just explained that. So I'm going to first in this lecture just talk about the limitations of PINs. We already touched on a few of them last lecture. And once I've given you what those limitations are, then I'm going to spend the rest of the lecture telling you about how we extend PINs to overcome those limitations. And the one that I'm going to cover in this lecture is mostly focused on the computational costs and how can we make PINs faster to train. And this is a really important thing to be able to do. By the end of next lecture, I'll give you a summary on the kind of realistic cases where you should use PINs and where you shouldn't use PINs, and you should have a good idea of when they're the best technique to choose. So yeah, you should be able to understand the advantages and disadvantages of PINs by the end of these lectures. And also in these lectures, there's a lot of current research on physics-informed neural networks. So you should be able to have a fairly good idea of the current state of the art in PIN research by the end of this. Okay, so let's just recap the advantages before we talk about disadvantages. And I talked a lot about the advantages last lecture. So here's a list of some of the biggest ones. As I've been trying to say, PINs are different than kind of traditional finite difference methods, for example, because they're mesh free. And this means that we don't have to generate a mesh when we're doing the simulation. And I told you in the course introduction, just the act of defining a mesh in your computer program can take humans like days or weeks, depending on the complexity of the simulation. So being able to not do that step is a big advantage if the PIN works. Another big advantage of PINs is that they can jointly solve these forward and inverse problems at the same time. So I was telling you how we solve an inverse problem with a PIN. We jointly optimize the theta values and the underlying parameters at the same time. This is kind of different to how we traditionally solve an inverse problem, where we'll have a forward simulator and we'll differentiate, we'll get gradients of that forward simulator. So in this case, we don't have to differentiate through the forward simulator, which can take a lot of time to do. So often they're best where we have these situations where we have some observations of the data, but we want to understand what the solution is. And maybe we want to understand what some underlying parameters are as well. One thing I didn't mention is PINNs also have tractable analytical solution gradients, which this is sometimes overlooked, but actually quite useful. So this just means that we can evaluate du by dt and du by dx, the gradients of the solution with respect to its inputs. And this can be very useful for doing, for example, sensitivity analysis studies on how the simulation might change depending on some inputs. And they're mostly unsupervised. If we think of PINNs from a machine learning perspective, we have this PDE term, which is an unsupervised regularizer. And so we can actually get away with training PINNs with very little data. And this is very different to these like big data regimes or ideas of training models. Okay, so we'll talk about the limitations. So there's three big limitations that I'm going to cover. The first one is computational cost, and I gave you a hint of this last lecture. I showed you an example of PINNs solving the wave equation. Again, we have like an earthquake or explosion in the Earth, so in some which we model with a velocity model, and the wave field propagates outwards and causes reflections and etc. And this wasn't a very big network. It was only like 10 layers, 1,000 hidden units. Like that's not massive compared to today's billion parameter models. But even just training this network to solve this simple kind of 2D problem, it took an hour to train on a GPU, and the finite difference simulation would take probably about a minute or less to run. So this just isn't competitive with a numerical technique in this form. The real killer is that once we change the initial condition, so if we try to simulate a source that's to the left or to the right, or maybe we change the frequency or something like that, the PINN has to be retrained for every new initial and boundary condition. So every simulation you run, you're going to have to retrain a neural network. Okay, so that's a big limitation. So let's talk about another limitation, and this is the sometimes poor convergence of PINNs. And it's not guaranteed that the PINN is going to converge to the minima of your loss function. And this goes back to our introduction to deep learning course lecture, where we talked about all these error sources. So, the finiteness of the training data, the approximation error of the network, and the optimizer, the optimizer might not be able to navigate the complicated loss landscape of that we're using to train the PINN. So, one of the biggest factors specifically when training PINNs is this issue of how to choose these lambda values. So I mentioned that the lambda values are very important because they control the balance between the boundary loss and the physics loss. So for example, if we choose lambda to be too small in this particular loss function, it means that we don't care so much about the boundary conditions, and we're only going to minimize the PDE residual. But that's dangerous because that means the network could learn any particular solution of the PDE, and it might not be the one that we want given the boundary conditions that we have. In the opposite, if lambda is too large, then we're not going to satisfy the underlying differential equation, and the boundary conditions might just be imposed everywhere in the domain. So I've got an example of this. This is again using a physics-informed neural network to solve the wave equation. Now we have a point source that's propagating through this velocity model here, which is just a couple of Gaussians, basically Gaussian perturbations. And you can see the wave field is like just propagating through these different perturbations and kind of squashing and changing its shape based on those perturbations. And this is the PINN. So the top row here is the ground truth finite difference modeling output. The middle row is after I've trained the PINN, after the final training step. This is what the PINN looks like. And at first glance, it looks like it does a pretty good job at estimating the solution. But what's interesting is if I look at the loss curve as a function of training step. So what I'm plotting here is the test error. So this is the difference between the PINN solution and the ground truth solution. averaged over all the points in the domain. And it's very interesting to see that whilst it does converge at a fairly low absolute error, halfway through training, the loss is still incredibly high. And if you look a bit further, it's very spiky as well. So what I would interpret this as is the PINN solution thrashing around. It's really trying to figure out what the solution is. And so it's interesting to plot the PINN's prediction of the solution at training step 20,000. So this is like here before it started converging. And what you can see is it's learned the boundary condition well, but then the rest of the domain, it's basically set the solution to 0. So anyone got any ideas why this is 0 here? Why it hasn't even started putting amplitudes in? Yeah.
That's how we initialize the weights.
Maybe. Yeah. Yeah, that could be a reason. It could be initialization. Yeah. Why is it, yeah, that's a good point. So why is it a local minima in the loss function? Yeah. You're on the right lines. There's another reason that that's related to that. Yeah.
So the way like 0 solution, trivial solution.
Exactly. Right? Yeah. So you've got it. So if you go back to the wave equation, a trivial solution of the wave equation is that u equals 0 everywhere. Like this satisfies the PDE constraint. It will give you exactly 0 in that physics loss term. So my intuition, my guess here, and I think it's correct, is if you think about the PDE term in this whole part of the domain, from this time point further, the PDE loss is basically 0. So it's very happy that it's minimized that term. The only problem is that there's some disconnect with the boundary condition just after the boundary condition. The PDE residual will be fairly high. But overall, the loss function is fairly well satisfied. So that is definitely a local minima, if you think of it that way. So this, you can see how this loss landscape is quite difficult and non-convex to optimize. Okay, the final limitation, and it's related to the poor convergence, is our ability to be able to scale PINNs to more complex problems. So everything, all the kind of applications that I've been showing you so far, I would argue have been related to what I would call very simplified or toy problems. So for example, waves propagating through just simple horizontally layered media, or maybe the fluid flow past a cylinder. This is kind of a canonical problem that we study in fluid dynamics. But if we talk about having, a significant impact in the world and having kind of real world impacts, what we really want to do is solve these like large scale problems that we care about. So, understanding or predicting how the whole climate system evolves, or for example, how earthquakes propagate through the whole state of California. Like if we could be able to solve these problems faster and more accurately, this would have a massive impact. But there's a massive difference between the left-hand side and the right-hand side. And if you think about our traditional methods that we would use to solve these kind of larger scale problems, it's often really challenging to scale them, right? This is why we're thinking about using machine learning to help, especially when we have multi-scale, multi-physics systems, if we have large or high frequencies, and if we have noisy and real or sparse data as well. These things can really make our traditional methods struggle. And I think it's a very valid question to ask. All these SciML techniques, even though they have some kind of interesting ways to put scientific understanding into our ML algorithm, how do they cope in these settings? Like, do they scale in the same way, or do they have different kind of limitations? And that's kind of an interesting research question to me. So yeah, how do PINNs cope in this setting? So unfortunately, PINNs struggle, especially in this case where we want to scale PINNs to higher frequencies. So what I'm showing here is using a PINN to solve, one of the simplest ODEs that I could think of, the u by dx equals cos omega x, right? So the solution is just sine. And what's interesting to plot is how the pin's performance as I increase the frequency of the solution. So as I increase omega here. So on the top left here is the easiest problem where the frequency is very low. So a frequency of 1 here. And I can train this very rapidly and very accurately using a PINN. And the PINN only needs 2 layers and 16 hidden units. And so in total, that's around 300 parameters to fit this sine wave using a fully connected network. If you look at the loss curve for this is the test loss as a function of training step. It's this red line at the bottom here. So again, it converges within a few thousand gradient descent steps and stays at quite a low level. But the real issue comes when I increase omega. And so if I go to omega equals 15, so a much higher frequency problem, the same PINN with 2 layers and 16 hidden units here on the top right really struggles to fit the solution. And in fact, it only fits maybe 6 or 7 of the cycles. So why don't you think that it can fit any more cycles in this case? Yeah, exactly. So we only have 321 parameters in this network. And so there's just not enough to fit all of these cycles of the solution. Yep. Yes. Well, yeah, absolutely. So the other question was, doesn't this show that the network doesn't learn at all, but simply memorizes? So I agree. I said last lecture, PINNs suffer from the same issues, estimation or error issues as standard neural networks. So they still have generalization error, approximation error, optimization error. And we're not telling the PINN that we expect the solution to be sinusoidal here. This is just a flexible function that's trying to fit to a sine curve. There are ways to put kind of understanding of what you think the solution will be into the PINNs architecture, and I'll talk about that next lecture, which can help. Yeah. So the only solution in this case, if we're stuck with using an MLP, is to increase the size of the MLP. So this is the plot if you increase it to 4 layers and 64 hidden units, and you can see it learns more cycles, but not all of them. And I have to push it all the way to 5 layers and 128 units, and this is taking over 60,000 parameters just to fit a sine curve. And even so, if you look at the training error, the test loss as a function of training step, even though it decreases, it's nowhere near as performant as the low frequency PINN. So I've got a little animation of this just to show you in an animation. And so this is a PINN training on this stamped harmonic oscillator problem. It's the same as what I've been showing before, but all I've done here is just increase the oscillator's frequency. So we're modeling out to more cycles here. And what's happening is the PINN is really struggling to fit the solution. So okay, so they're the 3 big limitations, I would say, of PINNs: the computational cost, especially for forward-only problems. For inverse problems, they're more competitive, like I said, because we don't have to run the forward simulator thousands of times. They can be hard to optimize because of these competing terms in the loss function. And they're challenging to scale to larger domains, like when we have high frequencies or multi-scale frequencies. So that sounds fairly dire, but the good news is that there are many PINN extensions, and there are many better alternatives than just training a fully connected network on the solution. So as I said before, this is a whole research field now in its own right, and this RICE paper has got over 8,000 citations now and if you go into those, there's hundreds or even thousands of applications and extensions of PINNs that people have shown. So we're going to talk about a few, some selected examples in the lecture. We can't cover everything. So I'm going to move on to talk about extensions for improving the computational cost, and that's going to be the rest of this lecture. Next lecture, I'll talk about those other 2 limitations, the convergence and the scalability to more complex problems. Okay. So computational cost, how can we improve this? So one big idea is this idea of conditioning the PINN on additional inputs. So it's a very simple idea. It's to say, instead of having to retrain our PIN for every new initial condition or boundary condition, why don't we just add those initial conditions or other PDE parameters that we want to solve across? It's just additional networks to the additional inputs to the network. So let's think about this seismic simulation task again. And this is our standard PIN where the only inputs to the network are the coordinates and the time value. And the output is the seismic pressure, essentially. So this is how a condition PIN might work if we want to train the PIN to learn across one of the initial conditions. So say that we want to learn a model that is able to predict the output no matter where the source location is. So what we would do is we would add the source location here, the X and Y coordinate of the source, as an input to the PIN. And then once this neural network has been trained, we don't have to retrain it on a new source location. We can query it at any source location and it will give us a prediction of the solution. Okay. So yeah. Well. Yeah. So I will answer that once I've talked about how we train it. But yeah, it's a good question. So so this is the loss function we use for the standard PIN. PDE, residual, and boundary conditions. And in this example, I just trained the PIN with a few time steps of the finite difference solution as the boundary loss. That was just how I defined it. So it's just trained on this red, essentially this red time step here, and it's learning to propagate outwards based on the PDE loss. So how do we train the condition PIN? So it's very simple, same loss function. All we do is we not only sample over the co-location points and the boundary points, we also sample over the sources as well when we're training the PIN. So let's think about the boundary loss. We have to generate lots of finite difference simulations with different examples of the source location to match now, because we want to generalize across the source location. So this is boundary loss is now matching the network's output across many different boundary or initial conditions from the finite difference solver. And then in the physics loss, remember this is still unsupervised, to evaluate it, all we needed before was random points of X and T. Now we also just randomly sample an S value, and we make sure that the physics loss is obeyed across all the S value inputs to the network. Does that make sense to everyone? So it's just simply adding an extra input to the network and training over it. So this is some work that we did. We tried to condition this physics-informed network on the source location. And we took this velocity model, which is a more complex velocity model than I've been showing you. And the white points here show you the source locations that we used as training points. So we carried out a finite difference simulation at each Y point here to get our boundary data. And then we randomly sampled across this area to evaluate our physics loss as well. And then the test runs here that I'm showing are just sampled from these red points. So kind of in the same distribution, but not exactly the same training points. And you can see that the PIN does learn to generalize across the source location. It is allowing us to evaluate the amplitude, wherever the source is located in this region. There's some interesting things here. So the PIN solution is not very accurate compared to the ground truth, actually. So what it does do is a good job of getting the direct arrival. So this like the main amplitude response of the wave, but it starts to really struggle with getting the reflections. And I think this is in part because they're much lower amplitude than the direct arrival. But what it does mean now is that this PIN doesn't need to be retrained for each of these source locations. So we can do some interesting analysis with this now. So for example, we can say, remember I said you have tractable solution gradients. We can say, how does the simulation vary as with the values of S? So if I change the source location, how does the amplitude change? Is it very sensitive or not? And this is a very interesting question for example, seismic hazards analysis, when you want to know what the amplitude response is at the surface. whether it's going to be a big shock if an earthquake occurs or not, and how sensitive is that to the location of the earthquake exactly. So this type of surrogate model where we've got a fast kind of approximation of the solution can be very useful in industry. Okay. Here's another example of a conditioned physics-informed neural network. So this is an example of using a depot net with a physics-informed constraint. And Sid is going to talk a lot about depot nets, and depot nets are more commonly known as an operator learning technique. And he'll talk about that from that perspective. But from this perspective, as a conditioned PINN, you can just think of it as a conditioned PINN, this physics-informed depot net. And so what is the network architecture? It's just essentially a fully connected network that, again, gives me a prediction of the solution of our differential equation here. And it takes in our x and t, our coordinates in our domain. But it also has a kind of special conditioning input that allows us to condition the output based on some function here. So that's the architecture, and this is an example of using a depot net to solve the reaction diffusion equations. So this is the reaction diffusion equation, and in this equation, U here would represent, for example, the concentration of some chemical reaction as a function of space and time. And what we're interested in doing is predicting the solution for different values of this function here, this f term. So the way the depot net works is it just discretizes this function over n points. So it takes n samples of that function as a vector, and that's the conditioning input to the depot net. And then the other inputs are these x and t values within the domain. And this paper trained this depot net using exactly the conditioned PINN loss function. So a boundary loss and a PDE loss. And this is the result they get. These are different examples of that conditioning function here, and this is the prediction or the exact solution and the predicted solution based on that conditioning function. So I put this example in because this is an interesting way to think about depot nets, and you can compare that to how Sid will describe them in the operator learning lectures. Okay, so the next way to speed PINNs up is to discretize their outputs. So this is what a technique, which is quite different, which I describe as discretized PINNs. And so what is the discretized PINN? So the idea here now is to say, instead of having a fully connected network that is giving us a functional approximation to the solution that we can query at any point in the domain, we're going to go back to just trying to predict the solution on a mesh of points. So we're going to have some neural network, and the output of the network is going to be a discretized solution. So a matrix of values, like, for example, if we want to solve the Burger's equation here, it would be 128 by 256 points. And the network that's going to produce this solution, for now, let's just say that it just has a fixed input. It's just maybe a random number or just a 0. And from that value, it decodes that value into the solution. So, for example, we could use a transposed convolutional architecture to do that. So the process of learning the weights is then to match the output to the true solution somehow. So yeah, to be very clear, that the neural network's outputs, the elements of that matrix, and now the solution at those grid points, and it's not a functional approximation. So this is the difference. So how do we train this network in a similar way to how we would train a PINN? And so we can use a very similar loss function to train this network in an unsupervised way, just like PINNs are unsupervised. So what we do is we say we have this output solution here, and we still want to minimize the residual of the PDE of that output solution. And we know that, for example, the Burger's equation here, we have to evaluate the gradients of the network with respect to t, with respect to x. So here we have a discretized solution. So the way that we can evaluate those gradients of the solution is just to take finite difference derivatives. So we replace our exact derivatives that we can get from a fully connected functional approximation to finite derivatives that we get from just taking differences on the grid. And it turns out that we can use this loss function and train this to match the solution, just like we can use this loss function to train the PINN. So to be fully explicit, when we're evaluating the derivative of the solution with respect to time, we just use like a finite difference on two elements, for example. Does anyone have any questions on that? That's a kind of a different way of thinking about this. Yeah.
What exactly is the input that you're providing over the
Yeah.
Just stated in say fixed value.
Yeah. Yeah. So in the simplest case, it's a fixed value and it can be anything. It doesn't matter what it is, but it should stay fixed. It should never change. If you think about the function that this network is representing, it's like a function, it's a vector, or it's a function that takes it takes a scalar value as input and gives you a matrix as output. And that function has some free parameters. But you just think of that as a black box function with some free parameters that we're tuning to make the output match the solution of the PDE. Does that make sense?
But like, what if I were to suppose change the input, let's say, so
Yeah.
then how would that change my solution?
Yeah, it would change it in a really strange way that doesn't make any physical sense. So we're only using the architecture as a flexible function. We're just hijacking the fact that it's a flexible function that we can train to produce a solution. We're going to change that in a minute, so it's going to make more sense. But this is the direct analog with it as if we were going to train a PINN. Yeah. 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 This could be thought of as a decoder, for example. Yeah. Yeah. But the difference is that this doesn't have any physical, the way that I framed it, it doesn't have any physical meaning at the moment. Yeah. Yeah. But you understand how we replace the exact derivatives with the finite difference derivatives. Okay. Yeah.
I'm start with the input conditions.
Okay. Yeah, so you got it. So we're going to change it now. Just before that, it's actually the one thing I didn't talk about was how we make sure that the solution obeys the boundary conditions. So that actually this is really important. I only showed you the physics loss here. What does the boundary loss look like? Well, we can't really have a loss function that asserts the boundary conditions here because well, I guess you probably could actually, but a better way to do it is just to make them hard constraints, because we can do that here. So we just add padding around the outside, and we just pad with the values that we know are the boundary values. So for example, we know the initial condition here that the fluid flow should start with a sinusoidal profile. So we're just going to pad the elements here with a sinusoidal function here. And likewise here, we're going to pad these values to be 0 to make sure the flow outside of the domain is 0. And you can see that when we start taking these finite difference derivatives, we're going to be evaluating the derivative against those padded values, and is what's going to constrain or make the solution converge to the particular solution. So this is kind of different to normal PINNs because we're having hard boundary constraints. We don't have that issue with the different lambda values in the loss function anymore. Yeah.
So basically,
Yes, but we don't solve the numerical method with like linear solves because the function that we're fitting is not like a linear function. It's like a complicated one. Yeah. Yeah, just for the boundary terms. Yeah.
It's just that the padding was just done so we don't have problem with ghost lines when we do the finite difference.
Also that, yeah. So this, you can see how we're getting closer to finite difference methods here. I guess the key difference is the function that we're fitting is like a nonlinear function. So we have to, when we train this, we still use autodiff. We still use autodiff here to update the weights. So we're still using the gradient descent to actually converge the algorithm. Yep.
doesn't leave it as a mesh tree.
Yeah. Yeah, so this now depends on the mesh, and this is a limitation of this method. Yeah. Yeah. Okay. So as someone suggested over there, what is great is now we can also condition discretized pins, just like we condition normal pins. And we change that input, instead of being some random fixed value, we change that input to be the parameters that we want to condition the discretized pin over. So for example, in the Burger's equation, you might want to be able to simulate over many different viscosity values and maybe many different initial profiles of the flow. And it's the same concept to condition pins, where to train this, we use the same loss function. We just, inside the loss function, we sample over all these different inputs when we're training the network. So we'll sample the physics loss over different viscosity values and different kind of initial conditions in the padding of the output. So now it starts to make more sense, I guess, that this is like a fast surrogate model. So what's the other way that you could train this, by the way? Just forget about this physics loss function. What we have here is a CNN that takes in some initial conditions and gives us a discretized version of the solution. What's the other way of training it? Yeah. Yeah, you could. So if you're given examples of this, you could try and learn this instead. Yeah, and you can directly learn a map. That's a really good idea. What I was thinking of is the simplest way to train it is just with a purely data-driven loss function, right? You can just generate loads of finite difference simulations and just train the network based on those. So what's cool about this method is that this doesn't need those simulation training examples. So we don't have to spend the expensive computation to get training data. So this is the one of the main papers that proposes this kind of technique, and it's yeah, a very influential paper. You definitely should read it. And one of the examples they showed in the paper was doing a conditioned discretized pin to solve the Darcy flow. So this is, given some porous medium, so this could be just a rock with fractures in, for example. Can I predict what the pressure is across that media of some fluid going through the media, and what the flux is through the structure of the rock? And yeah, what's really cool is that they trained this. So they used a more complicated architecture. It had convolutions and fully connected networks and other kind of things going on. But they trained it with this physics loss, so fully unsupervised, no simulation data required. Only requires input permeability fields as the input. That's the only thing you need to train this to converge. And they're using Sobel filters, which is just finite differences essentially to get the gradients of this physics loss. So here's some examples of the simulation. I think this is the prediction and the simulation, ground truth simulation. Looks like it does a really good job at modeling this flow. And they produced a couple of plots in the paper, which are quite interesting to look at. And so what we're comparing here is the test accuracy. So the accuracy averaged over many example inputs as a function of the number of training data that we have. So this is basically for the unsupervised discretized condition pin, this is the number of input permeability fields that we train it on. And you can see if we train it on more inputs, then the error decreases nicely, which is good. They also compare it to the data-driven version, which is the blue line here. So the data-driven version is when they've generated many thousands of example simulations using ground truth modeling. And what's kind of cool is that the unsupervised method is nearly as performant, especially when you have more training data, as performant than the supervised method. So you don't need simulation data to train these models. It's kind of cool to show that. What's even more impressive is if you test the network given some input that's outside of its training distribution, so the generalization error of the network. So say if I give it a permeability field that has way more channels or way more connections in the channels. They found that this unsupervised model, the discretized PINN, has better generalization performance than the model that's trained with only data, so the fully data-driven model. So that's kind of interesting. Maybe the physics loss is imposing more of a physics understanding into the network somehow. Okay. So advantages and limitations of discretized PINNs. Advantages, we can now start to use fancy architectures like CNNs to learn the inputs and outputs. And we can extend them to regular geometries. We can even do time-dependent versions of these with RNNs. But the limitation is that they require approximate gradients, and we're fixed to the mesh that we use. We can't change the mesh. Okay, I've got one more slide to show you before we finish. And this is training pins with finite differences. So the main reason why pins are slow to train is because we have to compute these gradients, the gradients of the output with respect to the coordinates. And I showed you last lecture that takes a lot of time to do. So the idea here is to not use autodiff to get those gradients, but instead use finite difference methods to approximate those gradients. And you can get kind of 2 to 4 speedups just by doing this. But the downside of this is then you're using approximate gradients, and this choice of this like width of the filter is a very important choice. Okay, so I've covered just the first extensions of pins, which improve the computational cost. Next lecture, I'm going to talk about improving the convergence and then also the scalability to higher frequencies. So yeah, thanks for coming. See you next time.